Okay, so we can start our afternoon session with Yannick Herfray. He will talk about infrared divergences in gravitational scattering and BMS representations.
Yes. Okay. So, well, first of all, thanks a lot for the organizer for making sure that, well, for making this month of a program possible. I've been really enjoying it in the last week, so thanks a lot. And yes, so I want to talk about some work with Xavier Beccart and Laura Donnet, and this is work on, so in this recent paper, we investigated BMS particles, by which we really mean unitary irreducible representation of the BMS group. We are not the first to be interested in these things, so the name and concept we borrowed from Blagoyer Oblak thesis, BMS particles in 3 dimensions, where they, well, actually, it's close and different because there they were really interested and focused on the representation theory of superrotations, while in this work, as I will say several times, we stick to the old BMS, but in 4 dimensions. But this, again, we are not the first to be interested in. Representation theory of BMS4 has been studied carefully so there is even a classification in a certain sense, hopefully I will have time to discuss that, by McCarthy in the series of work in the 70s, with important contribution from Girardello and Paravincini. And so, yeah, so the main objective for this project was to reconsider this classical result, but in light of the new understanding that we have from the last years. And here are a few of the outcomes that came up from this work. So first of all, we want to advertise the decomposition of supermomenta in terms of hard and soft pieces that is very natural and sits with the, in light of what we understood on hard and soft particles, these sort of things in the last years, but that McCarthy could not, well, never considered. One thing that we really wanted to do, I mean, that was the start of this project, was to be explicit about the construction. So if you look at these papers, they are very deep, a lot of new results, but they are very abstract statements, like existence, so to speak, results. It's pretty hard to from just hearing at the proposition and theorem of McCarthy to get a feeling of what you're supposed to compute, what these states are like, and what they are supposed to tell you. So one of the things that we really wanted that we do in the paper and that we worked out carefully is explicit realization of the wave functions, explicit realization of the branching rules in particular under the Poincare group, with algorithmic procedure on how you're supposed to branch a given BMS particles inside into Poincare particles. Another thing that comes out from this work is, in particular from this decomposition, is the possibility to get some flavor of what a BMS particles is supposed to be. Because again, if you just look at McCarthy's paper, it's some abstract statements. It's very hard to, beyond some very specific example, it's very hard to get any flavor of what these other representation, are trying to describe. And we think that it's one of the messages that there is a sense in which you can think of all of these BMS particles as a bunch of Poincare usual particles, but just sitting in all possible gravity vector. And in particular, the sort of the states that are constructing in this way, they are very similar to ideas and intuitions that Capek and the collaborators studied in these works. Okay, so this is like the overview of what we did. Hopefully, I will give more details. Absolutely, yeah. Well, we'll get some. Well, okay, that's in particular. I think I want to have a discussion with everyone about what we mean, what do we mean. So technical details have been presented by Xavier last week. So I'm aware that a lot of you were not present last week, so I will give again some technical details. So sorry for those that were there, but okay, so there will be overlap. But also today, something that was not really emphasized last week, and I want to take this occasion to have a discussion, is motivation of the construction, in particular in motivation starting from in relationship with the problem of higher divergences. And in particular, last week we had discussion about this, and hopefully we can come back on this and clarify what, in particular with respect to gravity vector, what we think is happening. Okay, so let's try to do this. Let's discuss a bit of infrared divergences from that perspective. So we know that the reason why infrared divergences they arise in QED or in general in any theory with long-range interaction is the problem that asymptotic states that the asymptotic state of the interacting theory cannot be the asymptotic states of the usual, of the free theory, because precisely we have long-range interaction. So this is why if one is not willing to give up on the S matrix, so most people give up on the S matrix, most people compute cross sections, and that's perfectly fine. But if one is not willing to giving up on having an S matrix scattering between states, then the asymptotic states needs to be modified. And this is what people suggested very early on in the work of Chung, Dollard, and Fadeev Kulish. But if you do this, one thing that I think you always need to keep in mind is that it's not that you're changing your states. You're genuinely changing the Hilbert space that you are considering. So the Hilbert space, if you want to consider any of these states that a lot of us like Fadeev Kulish, you have to change the Hilbert space itself. You're not working with the Fock space of the free theory. It's some much more complicated Hilbert space that you're considering. So this was advertised very early on for QED by Kibble, and for gravity, Ashtekar also very strongly emphasized this point that you need to go away from the usual Fock space to define scattering. And in both cases, the perspective was that if you want that in your Hilbert space, you want to have states which are coherent states, allowing for, today we'll say allowing for memory in the coherent state, allowing for memories, you need to depart from the usual Fock states. And these Hilbert space were explicitly nicely realized by Prabhu, Sachandran, and Wild with the modern methods of GNS. This sort of methods. Also, what this means in practice, it's actually very hard to compute infrared finite scattering amplitudes. As far as I'm aware, there were very few examples ever computed. And 3 weeks ago, we were in CERN. There was discussion on infrared effects. And as far as I understood from the discussions, there are only these 2 works that ever computed the scattering finite amplitudes. Okay, and part of the difficulty is that these Fadeev Kulish states, they are coherent states. There is a lot of room, there is a lot of freedom in what are the type of states that you might want to scatter. So it's not even clear what you want to compute in the first place. Okay, however, in the meantime, we learned something. That's maybe what I would like to have a discussion with you today. We learned that the BMS group is a symmetry of the S matrix. This is identical to statement to Weinberg's theorems. So the gravitational S matrix is BMS invariant. So the question is, how far is this statement constraining the Hilbert space that we want to use for scattering? It's not an obvious statement because a consequence of the way you prove the equivalence between wild identities and soft theorems is the fact that the soft charges act non-trivially on the vacuum. It inserts gravitons. So it smells like spontaneous symmetry breaking. However, as we know, in gravity is different from our usual spontaneous symmetry breaking because we know that there are physical processes that can change gravity vector. And moreover, physical process of finite energy. So it's different, definitely different from the usual QFT situation where we have gravity vector where no physical process can relate one to the other. Here it would seem that there are physical processes doing this. Another point is that the typical states that we like, that people use to construct infrared finite scattering amplitudes, so the Fadeev Kulish states, as a generalization, in particular generalization from these works, these states, they are eigenstates of the soft charges. So if they are eigenstates of the soft charges, means that they have to, by definition, to span a little bit of all possible gravity vector. So they cannot be just stuck in one super selection sector, but they are everywhere. These states, by definition, they are everywhere on all possible gravity vector. So, okay, these facts, they suggest that there are no super selection sector with respect to, we have symmetry breaking, but it suggests that there is no super selection sector. This was already argued in the lecture notes on infrared structure of gravity by Strominger. Okay. So, and I think last week there was a bit of a confusion about these states, whether or not there was super selection sector. again, I think these states, this is, and I've never heard of anyone claiming that they are superselection sectors strictly, in the sense that gravity vacua, you are not allowed to, right? Yeah, please. Yeah, yeah, yeah. Mm. Very good. I think the question we want to ask is, these states that we like, they belong to an Hilbert space, and what's the structure of this particular Hilbert space? I think that's the question I'm trying to ask here. And again, obviously from the title of the talk and where I'm going, the question is that, is this big Hilbert space in which this Faddeev state lives, is it a representation unitary of the BMS group or not? And I think, as far as I'm concerned, this seems to be an open question. And what you're saying is correct, but I don't think it's really addressing that particular question of what is the structure of the Hilbert space that we are trying to gather from. Yes, please. Okay. Okay. Okay, very good. So I think it's a different point, right? So what I was saying is, if we are thinking of if you have a symmetry breaking, usually you would think that a super selection sector has to do with gravity vacua, and then but then the eigenstate of soft charges, they cannot be in a definite gravity vacua, right? They are in all possible gravity vacua at the same time. So that's what I meant. Now, you're suggesting something else. You're suggesting that super selection sector should be eigenstate of soft charges themselves. I agree, it seems like an interesting idea, but wouldn't you agree that, I think as you explained in your paper, right, that the Lorentz group acts on the soft charges, and it takes you from one of these pairs to another one. So I think that if we really believe this, that each of these eigenstate of soft charges is a super selection sector, I think it's saying that the Lorentz group is broken, no? Isn't it what this is saying? Because if we believe that the Lorentz group is unitarily implemented on the Hilbert space, then this cannot be super. It is. L or, yeah, any. True. Right, but this is always effectively choosing a gravity vector. I mean, by definition, right, choosing a Lorentz group is always a choice of gravity vector. True, but you mean by definition you're making a choice when you're doing this, right? It's a choice. By definition, you're choosing a gravity vector when you're doing this, right? So it's just. So wouldn't you say? Wouldn't you say? So very good. Yes. It's not in BMS, so there is a bigger group. You're saying there is a bigger group of symmetry, like the universal enveloping algebra of BMS, that you should consider. Is it your suggestion? Okay, well, I'm not sure I understand the construction. At classical level, is I think you okay. Yeah. So I see. So you're saying there is never any BMS group. It's always Poincaré. It's a different Lorentz. It's living somewhere else. Okay. Okay, so it's different symmetry. So okay, so in that sense, it's not even related to what I'm discussing so much. It's a different symmetry, like an extension. Okay, very good. Okay, interesting. Maybe it could be the right one. Okay, okay.
Like Lorentz, when you do a non-gate covariant gate choice, the usual Lorentz has been in. It seems that it's problem with gate choice, but it's not because we say the bigger rule. We say the enveloping algebra of the bigger, it's a gauge algebra plus Lorentz, there is a generator that stays.
Okay, so very good. So another proposition, you can look for enveloping algebra of this and this. Okay, well, why not? But then we need, okay. But you, about your suggestion, would you agree with that? It cannot be strictly speaking that each of the soft eigenspaces, I mean, soft charge eigenspaces can be super selection sector.
I'm talking about charges in the spatial fluidity. I'm not sure that it corresponds to your soft charges, but I agree that if that's non-zero, then you don't have, that screw will take you out of the super selective gauge invariant observables will be super selective, but the Lorentz group will take you out of it. So I think I'm agreeing what you're saying. I mean, except for the zero charge.
Yeah, which is very special, and as you observed in gravity, cannot be, doesn't make sense. Okay, so a possibility, as far, I mean, this was, or we want to consider this possibility that the BMS symmetry is unitarily realized on the Hilbert space, that maybe this gives different way of organizing this complicated Hilbert space of coherent states, and that has been constructed in different other ways. And this, it's an important question to clarify between us, because obviously, part of the reason why symmetry are important is the fact that you have symmetries. If you have a symmetry unitarily realized on the Hilbert space, is a very strong constraint, because it means that then it's representation. Representation theory is very constraining game. From that perspective, it's actually I feel it's an appealing possibility that it could be the case. Maybe it's wrong. Maybe it's another group acting. I think. But this sort of question have to be addressed. So in terms of the QFT itself, it means that you need to think differently with your notion of particles, because they should be representation of the BMS group rather than Poincaré particles. And even in terms of holography, it means that your states should be organized by the BMS, as unitaries of the BMS rather than just your usual Poincaré states. Okay. So, so this is motivations. So let me now get to the more technical details of what we've been doing. So we want to discuss BMS representation. So let's talk a bit about BMS group itself. It's just to fix notation. So what I'm going to write like this, curly EW, are conformal weights delta equal minus W. It's just the conformal geometry notations. I'm so used to it, I can't really change, but it's minus as opposed to the CFT one. And a classical statement is that the Poincaré group sits inside BMS, but this inclusion is not unique. And this is what I call gravity vector. It's So this is one definition. This is this coset. It's a choice of Poincare group inside BMS, which is never unique choice. Nevertheless, there is quite a lot of structure that is invariant. One is this inclusion, so inclusion of translations inside of super translations. So and this will be realized by this object R. So R4 sits inside E1, super translations. And what's interesting is the dual picture of this, is that in the dual, so the dual of super translation would be super momenta. So, and the dual picture is that there is a projection. So there is a projection of super translation. So E, which will be E minus 3, it projects on usual momenta, so R4 star. So that's useful facts to keep in mind. So, and in practice, the projection is just this integral. You take your favorite super momenta, so it's a weight minus 3 object on the sphere, and you get this momentum. Yeah. Sorry. Well, I will explain again, but I mean, so in the following sense, is that you will have a pairing between super momenta, which are functions on the celestial sphere, and super translations, and the pairing is an integral over the sphere. So dz of curly p z bar, and t z bar. So this is conformal weight 1, and therefore for the full integral to be a scalar, this needs to be conformal weight minus 3 because the volume itself is conformal 2. So in this sense, these are dual elements. Genuinely, as we will discuss, you should think of super momenta as being distributions. But as a starting point, it's good to think of them as just being any conformal weighted functions. Genuinely should be distributions with the right weight. Okay. Okay, so what's the classification of McCarthy, the classification result for McCarthy that we had? Okay, so first of all, it's a list of papers. There are a lot of results here and there. So let me try to clarify what is where. So in the first 4 papers, what it does is that it gives you a complete classifications of all BMS representation for integrable super translation. So it's an infinite dimensional group. So the topology is a subtle question. So you need to say what you call BMS. In this first paper, he claims that BMS is super translation for L2 squared function on the sphere. And when you do this, you can go very far. You completely classify everything. The physical claim was that, well, it's great because it only allows for compact little groups, and therefore you're excluding tachyons and you're excluding continuous spin particles. Okay, very soon it was realized by these people that this was all about just this unnatural requirement of asking that super translation are square integrable. If you're actually only requiring that your super translation are smooth, well, then the duals change. The dual is genuinely a distribution space, and you have a lot more representations, and this is what this Girardello and Paravicini pointed out. In fact, in retrospect, when you look at all these works, this initial assumption is very bad because it's excluding all possible massless representations. So it's not just about tachyonic and continuous spins. All massless particles are excluded. So genuinely, if we want massless particles, it's very important to consider smooth super translation in the dual distribution on the sphere. Okay, then once this has been realized, in the later works, McCarthy considered classification for super translations which are distributions, super translations which are smooth. This is what he called nuclear topology. It's a barbaric word for just saying that super translations are C-infinity. And you get a classification. In this case, strictly speaking, the classification is not completely proven to have all possible representations. So it might be that there are other very weird representation of the BMS group for smooth super translations, which are not appearing in this in the language that he describes. There is some loophole in the proofs. In this topology, so by just it's just a fancy way of saying that you want smooth super translation and not just square integrable. Then you have all possible, you have representation that you like, meaning both massive and massless. And he corrected also some errors later on, small stuff. Okay, so what's the result about? How does that work? So let me try to sketch it. So it's an induced representation method. To get a flavor of what's going on, it's good to compare with the Poincare one. So what do you do in the induced representation methods for Poincare? You have translations, and the first thing you do is you consider momenta, which are in the dual of translations. So for BMS, this is where things get slightly more interesting, is that now super translation is infinite dimensional. As we discussed, there is even an ambiguity by maybe what you mean by super translation, but the pairing is an integral over the sphere. And in general, again, you should think that super translation is some sort of distribution on the celestial sphere. Okay, next step is you fix an orbit. So in practice, you choose some reference momenta that you like 1000 or 1001, and you act on it with the Lorentz group, and it produces for you some orbits into the momentum space. So these are mass shell. So you're producing the mass shell by acting with the Lorentz group. The thing which is classifying the shape of the mass shell is the little group. And so in practice, if you can find all possible little groups, you have all form of the possible mass shell. So in the usual story, it's just SU2 for massive field, ISO2 for massless field, SL2R for tachyonic representation, and there is always also the very degenerate zero momentum representation. So doing this for BMS was the heart of McCarthy's paper. So you should do the same. So you fix an orbit, by which in practice you mean what you have to do is you fix some reference super momenta that you like. And then you act on this with the Lorentz group. It produces an orbit for you. So you should think of it as a mass shell in the infinite. You have this infinite dimensional space of super momenta. And by acting with the Lorentz group, you're producing a finite dimensional mass shell. And the heart of the McCarthy works is to figure out all possible little groups that might appear here. And the heart of the proof is a proof by exhaustion. So it's just saying, okay, SL2C is a group that we know. There is a classification of all possible little groups. He tries them all, and he excludes the little groups which are not actual little groups. And at the end of the day, he is left with 11 possible BMS little group. So you have 7. There will be a list on the next slide. One thing to have in mind is that the mass shell are always of finite dimension because they are just produced. This mass shell, quote unquote. I mean, the space on which the orbit are always of finite dimension, just because they are orbits and they are always homogeneous spaces. So they are like something like this. Good. So now, what are the wave functions? The wave functions, they are now functions with support on a given orbit of the Lorentz group. So the usual Poincare particles, you take your mass shell, and you just wave functions are function on these orbits, and then the spin of the particle is by definition a choice of unitary irreducible representation for the little group. For BMS is the same. So wave function, a BMS wave function is a function on this extended orbit. Now in general, you are going to have more extra degrees of freedom for this other more surprising representation. And again, what you want to call the BMS spins in parallel is a choice of unitary irreducible representation for this BMS little group. Sorry. What does the what? The little groups. Yeah, this is next slide. So this is the list. So this is the main table in McCarthy paper. So not only it gives you the little groups and also representative, so super momenta, which are realizing these little groups. So you have the 4 little group from Wigner, and I will come back on this. When you have as I will explain, if you have a representation for which, well, it's almost okay. Well, part of this representation will be the usual representation of Poincare that we like, but then there are others, and then you can have R2. This is R plus times U1. This is you can think of it as C star with the multiplication on it. And also other little groups. In particular, there's a little group which you would never think of in the usual Poincare representation, is the trivial little group. Actually, if you take a generic, you just take a function on the sphere, a distribution. Well, what's the stabilizer? Most of the time, you'll have no stabilizer whatsoever. So massive, the vast majority of VMS representations, they are like this. They have trivial little groups. And from that perspective, the other one are very special. Representation for which the super momenta has some symmetry. They are exotic in that respect. However, the point is that since the whole work of McCarthy was to classify these little groups, he's never talking about these ones ever in the paper, because for him it's like the obvious case. And he's spending a lot of time trying to convince you that all these representations, they are what matters. But again, I think we should be careful about this. All these super momenta, all these representations with special little groups, they are oddities as compared to the generic case, which have trivial little groups. Yeah. And, Lorentz group, because this is induced representation methods. So it's like in Poincaré, you choose a momentum and then you look for the orbit of Lorentz group. So that's why that's why this is tractable. So if you were to try to look, so for example, in some of the work in the literature, people try to use quadrant type of methods. It's much more difficult because you need to look for the adjoint of full BMS inside of the dual. This is very hard. McCarthy's method is much more pedestrian, and that's why it can work. You're really genuinely working for an orbit of SL2C, finite dimensional, and that's why you can actually do something. Yeah. Okay, so in practice, the way, okay. So precisely exactly what we are going. So part of the question is what's the physics follow this. So the type of things that we can do is the following. That we check is, you're going to have a generic BMS representation. The full BMS group will be acting on it. At the end of the day, the states will have full representation of the BMS group. Now, you would have gravity vacua in the sense that if you want to branch, if you choose a Poincare group inside BMS, and you're trying to read off the spectrum of these BMS particles in terms of the Poincare subgroup, you would get branching rules. This is one of the things that we spent a lot of time in the paper making very explicit. So you can branch your particles, and this will be like reading your particles in a given gravity vacua. And then what's going to happen for a generic BMS representation is that it's going to depend on your gravity vacua. If someone else comes and say, well, look, I'd rather take this other Poincare group that I like, it's another gravity vacua, you will open up your particles in a different way and you will see a different field content. That's the sort of phenomena that can happen. Not sure, yeah. I think to which extent the physics is will be right is another question. So I'm not quite sure what you're doing. So again, I think just to be clear, in the case where supermomentum are L2 function on the sphere, the claim is that all possible BMS representation are constructed in this way. And then you can ask which one are physicals, are relevant, which one I want to use. But at least when the supermomentum is in L2, so super translation are in L2, therefore supermomentum as well, you have all of them. So it's a classification result. So very good. I think I'll try to come on this. The part of the work was maybe try to clarify this sort of statement. I'll come on things which looks like what you're saying. Yes. I mean, part of the question is, I think this is what I tried to discuss in the first part of the talk. Is part of the question is, do we believe that what we call the vacuum state is a unitary representation of the BMS group? If it is, it should sit somewhere in here, and there are states indeed in here which looks like gravity vacua. But I think this is to be. I mean, the exact physics, I think, is open. That's what I want maybe to discuss with you today. Okay, so just to say, so precisely, I mean, at this level, this is not very, this is the essence of McCarthy's result. Here, so the main message is that we have 11 different connected little groups. Again, I think it's very important to keep in mind that the most generic little groups is just 0. It's like trivial little groups. There is a quadratic Casimir invariant playing the role of mass. And this is due to this projection. If you have a super momenta, you can project on momenta, compute the mass of the momenta. This is a quadratic invariant. So there is a sense in which it's meaningful to talk about the mass of a BMS representation. It makes sense in this sense. Okay, so it's a classification, again, similar to learning that mass and spin are a thing, but what does the state look like? What is it telling us? And that's part of the thing that we are trying to address in this work. Okay, so first thing to have in mind to ask this question is what we call hard representations. And they have here is exactly very precisely what we mean. So it's known since Sachs and then Longhi Materazzi that absolutely all usual Poincare representations, they all lead to BMS representations. So whenever you see a Poincare particles, you can think of it as BMS particles. It costs you nothing. You can always do this. And this was realized explicitly by Longhi Materazzi. We had a nice talk by Joachim last week on discussions around this theme. Yeah, and so they are very specific BMS representation. So among the flurry of BMS representation, you have these representations which are very specific, which are the ones which are coming from Poincare particles. They are specific. They have little groups SU2 in the massive case, ISO2 in the massive case. So there are situations where the BMS little groups coincide with the Poincare little groups. Yes. Please, please. That's right. That's right. Very good. Okay, so okay, so there will be a slide where this would be explicit, but just to say, so in this paper, they were absolutely not thinking of asymptotic symmetry or whatever. So I think it's just a very clever guess that they realize that they can do it, that you can extend representations. You do it in Fourier modes, I will show you it. But then most recently, it was explicitly done by Campiglia and Lada, where they take the massive field, they go at time like infinity, they realize the BMS field, the BMS symmetry at time like infinity, and then you see that you can act with asymptotic symmetries on the massive fields. And then we also have a paper with one of my students where we try to geometrize this to the very end by thinking of it as a field on an extended boundary at time like infinity. So there are different ways of realizing this like more geometrically. But you will see explicit expression like probably next slide or something. I will show you something very solid. Yeah, okay, that's what I want to say. Then you can realize this in terms of scattering data on asymptotic boundaries of Fourier modes. Yes, so here it is. So you start with your usual, let's say just scalar field, but again, it works for every representation, including continuous spins. Even though I think for continuous spins, the geometrical realization is not known. So the similar statement of what I'm saying here, I don't think is known for continuous spins. Okay, so for scalar fields, as we have been told, it's the classical story. You go to scry, then the field is some field at scry, and you just act with BMS on the field, and it gives you a phase. Okay, by the way, what is this phase? This phase, you should think of it as some duality pairing between some supermomenta and a super translation. So this is what we call the hard massless supermomenta. This is this delta function. Now for massive scalars, so there are different ways again of geometrically realizing this, but you can just guess it from as Longhi and Materazzi did by realizing that if you take a propagator on the hyperboloid, and you contract it with the super translations, then it gives you a number. This is what you use for your phase. And this is the action on the massive modes. Now, here, this guy looks exactly like a pairing like this. So you can just read off the hard massive momenta, and this is this object. And these objects we've been used to use these objects in the context of asymptotic symmetries, etc. What they are from the perspective of representation symmetry of representation series, that they are the supermomenta of your usual Poincare particles. So these representations, they are very special. They are very special supermomenta. They are what we call hard, and I think it's clear why they should be hard. They are the supermomenta just coming from your usual Poincare particles. Just take your usual Poincare particles, you have these representations. That's it. You get it for free. What you do not get, however, okay, so at this stage, you might think that, okay, if I can do it for free, why should I consider other representation? There is a subtlety about this construction, is that this map, the map taking momentum to super momentum, is a nonlinear map. It's obvious statement here because, for example, here it's just there is some p to the minus 3 appearing. Here it's a complicated transformation taking you from omega q to this delta function. By the way, this is massless. This is the hard supermomenta of a massless particle. So it's a distribution. So this is where you see that if you're trying to kill, to restrict your representation to only L2 super translations, distribution are not allowed, and you're just killing massless field. Again, however, this is a non-linear map. What this means is that even though you can, if you're imposing conservation of momentum, you will not have conservation of supermomentum, just because this is non-linear. So there is no way, in general, this will just never be true. In the case of massive representation, this remark was made by Chatterjee and Lowe quite early on. But it's true for, it's just a general statement that just hard super representation. Let me try to make this point clear because I think it's important. So you can, for free, go from usual Poincare particles to BMS representation. Cost you nothing. However, what it costs you is that only with these states, you cannot preserve supermomenta. It will not work. So therefore, the moment you're thinking of your states as being Poincare particles, you're forced to go away from these states. You're forced to consider other type of states which are going to be representation which are not of this type. Otherwise, you cannot conserve supermomentum. Sorry. What? That's right. You cannot conserve supermomentum with these states alone. From that perspective, yeah, yeah. So I mean, from that perspective, again, if we want to take serious, if we consider, and again, I think it's open question, that we are thinking that genuinely we have an Hilbert space, that the BMS group is acting unitarily on this Hilbert space, then just these states are not going to be enough. Soft theorems are telling us that we need to go away from this representation. We need to consider other type of states, which are going to be more exotic representation of the BMS group. Maybe, yeah. So yeah. So what? Okay. What other type of states? So what? How can we go beyond our representations? What can we learn of going beyond that? So yeah. So one thing that we think is an important point is that supermomenta can be decomposed into a hard and a soft pieces, and it's not okay. So this decomposition is so again, what we call hard is just usual. It's supermomenta of usual particles, of usual Poincare particles, but now thought of as BMS particles. And then what we call soft, these guys are supermomenta which have zero momentum. So supermomenta which are like this, they are supermomenta which such that when you project, they have zero momentum. So maybe this you might want to call gravity vacua in the sense that they are going to be states which are zero momentum representation from the perspective of the Poincare group. I think again it's open to which extent these are the correct states that you might want to scatter or not, but they exist, these representations. A point here which is important about this decomposition is that, okay, it's unique, it's Lorentz invariant. By this I mean as opposed to, for example, a spherical harmonic decomposition, something that we like to do when we are in this context of having like a BMS charge, is spherical harmonic decomposition. Spherical harmonic decomposition is not Lorentz invariant. So just saying, just trying to say that you have a hard part and a soft part in general is not Lorentz invariant statement. Here it is. The price to pay is that it's a non-linear decomposition, as I already emphasized. Yeah, sorry, should have said already. So this guy, as already emphasized, this part is non-linear in the momentum. What this means is that this decomposition is not a decomposition of vector space. I'm not saying, because it would be wrong, that there is a Lorentz invariance. You can write supermomenta as a direct sum of Lorentz invariant pieces. It's not correct. Nevertheless, this decomposition makes sense, but because it's a non-linear decomposition. And this is what I said before. Just adding, another way of saying it is that the subspace of hard supermomenta is not a subvector space of supermomentum, as I discussed before. If you scatter two hard supermomenta, you would get something soft out of it. Soft in the sense that a piece like this. Okay, so it depends what you mean. So I mean, if you're asking, can you show me a representation? I mean, one of these non-hard BMS group representation in a physical context. I think right now I cannot answer positively. I think this is to be worked out. Like from that perspective, these representations are there. So maybe they are useful. Maybe we should produce some models or something which is producing those states. So I cannot give any dynamical realization of these objects. This is your question. But of course, yeah, I mean, so from that perspective, that's why representation is interesting. It's like classifying something, and then you realize that there's something that maybe you never look for. Yes, please. Well, I think everything is possible. So if you're thinking that you're just trying to scatter hard states, then and that you're thinking that the representation coming out is just going to be a purely soft representation, then that guy is completely fixed. But something that could happen, and I want to emphasize this, is that it might be that you're going to have a representation popping out, which is neither hard nor soft, which is something, a superposition of those. And these representations exist. I will make a point on this one. And they are different. They are different type of beast. Again, maybe they are not the right physical one, I don't know, but there is far more than just hard guys and just soft representation. There is a whole zoo of stuff in between that's, and yeah, I'm not sure how you're supposed to interpret those, please. You could imagine, I think that's what I'm trying to say. You could imagine having zero soft, only hard representation at square minus. So only usual particle at square minus. You're trying to scatter them. And then the point is that it cannot be that the outgoing particles are just going to be hard representations. It's not possible. You're forced to consider other representation which are soft. This is forced. Again, I mean, if you don't believe that BMS group act unitarily, then you don't need to do anything. But if you believe that the BMS group, that the Hilbert space of the outgoing particles carries a BMS representation, you're forced to consider this other very strange representation. I think that's the content of our understanding of soft terms. And again, well, maybe that's the next slide. Yeah. Okay, maybe I should have said already. So an important property of this decomposition is that when you project on the momentum, this is a zero momentum type of object. There is zero momentum in this part, and this is just a nonlinear realization of the momentum of the supermomentum. Okay, so yeah, something I really want to emphasize, because from the intuition that we had in the literature, it's something that is not natural, is that sure, we have these hard representations. They are just the usual Poincare representation in disguise. This is just a fancy way of thinking of our usual Poincare representations. Okay, now there are these other representations which we call soft, and we call them soft because they are zero momentum representations. They have zero momentum, so there is no energy, no momenta. But also, you have all these other representations where you have both at the same times, and they are something else. They are, okay, of course, you can try to cook up such representations by taking a hard one, taking a soft one, taking a tensor product, and it feels a bit like dressing, but there is something, you can also think of this representation as just being out there, and maybe this is a different type of particles which is at the same types, hard and soft. It's hard to even phrase in our language, but that's what representation theory suggests. These states, they exist. Again, whether or not they carry some physics to be worked out, but because of this, it means that you can't just take hard particles and just add one soft. It might be that you need to add different, maybe maybe you should think of this as some sort of dressing of your hard states by something soft. I don't know. But I mean, part of the result is to advertise that these representations are out there. Maybe they are useful. Maybe you should make use of them somewhere. Yes. Can be anything. So okay. So good question. So okay. So something that we prove is that because this decomposition is unique, the BMS little group must be the intersection of the little group of this guy and the little group of this guy. These guys, they always have either SU2 or ISO2. So in this object, they can have any sort of little group. So it can be trivial, could be any of the one in the McCarthy's list. Okay, essentially. But generically, you should expect that you have no little group. Again, you should expect that there is no symmetry in this soft part, I think, generically. Okay, so so this is about this decomposition of supermomenta and trying to get a flavor of what hard and soft in these representations. So another things that you can consider are BMS wave functions. So at 0th order, this has to be something like this. So just like our usual Poincare particles, they are superposition. You write them in the momentum basis and take a linear superposition with your wave functions. Here you're going to have your wave function on supermomenta, and you have this sort of object. But now, as we discussed, supermomenta you can decompose into a hard part and a soft part. So it's much better to write it like this. So you have one part of your integral which is over the hard degrees of freedom, so momentum. And then you have another part of the integral which is only going to act to see these soft charges. And so you have other degrees of freedom, and typically, so okay, here I wrote it as a path integral, but generically it's a finite dimensional integral because it's just an orbit. And so these extra degrees of freedom, they are moving this soft charge around. And yeah, again, part of the energy that we put in the work was trying to construct explicit examples, with all sort of, writing integrals which are explicit, that you can actually see what's going on. In particular, once you're here, you want to see, as I discussed before, branching. So now you choose a Poincare group inside BMS group, and you're trying to read off the field content of these guys in terms of Poincare particles in a given gravity vacua. And by here, gravity vacua, I mean, again, I choose a Poincare group, and I'm trying to interpret by BMS particles in terms of that particular Poincare group that I selected. Good, but this is okay. So that's already interesting, because you can write this guy and think of the branching rules. But now you can, once you understand this, you can go a bit further and play around with Fourier transform to give to get some different feeling about what these representation are about. In particular, one thing you can do is do a half Fourier transform. You keep momentum fixed, and you Fourier transform the soft part of the momenta. In the dual, it's a gravity vacua, by which I mean exactly this object. So an element in the quotient, so it's a Goldstone mode, or an element in the quotient of BMS Boy Poincare. And then, okay, so you take this guy, you dualize, and now your states, they look like this. They look like wave function on the space of momenta and gravity vacua. Now this is genuinely a path integral, so this is much more formal. However, these states, they are on shell, in the sense that you have to remember that genuinely in the supermomentum space, they are finite dimensional integral. They are finite dimensional integral. In particular, these states are normalizable, in the sense that the norm is the square of this guy integrating on the mass shell. Okay, so that's why, I mean, when we started all of this, it was very not obvious that yes, yeah, I think, well, I'm done. So actually we'll have some more time for discussions. So that's why, so that's why when we started the project, it was very not obvious that you could get any flavor of what these states are about, because when you read McCarthy, they are just things which are classified by some little groups, but no idea what they are supposed to maybe physically mean. Here, it starts to have some physical flavor, because it really looks like a state is some wave function on the space of gravity vacua and momentum, which is on shell in a particular sense, in the sense that when you Fourier transform, it lives on a finite dimensional manifold. Of course, as maybe Joachim asked, it would be very interesting to understand in which sense these are on shell states. But there, you need to give some meaning to what does that mean to be on shell when you are a wave function on the space of gravity vacua. We are not there yet. However, this picture, the type of states that you're getting from there is a very similar picture from the paper, again, as I already said, from the work of Dan Capek and collaborator, where you have scattering amplitudes living on the space of gravity vacua. It really feels like the same type of object. Okay, and yeah, so that's it for what I want to do. So of course there would be it's just the tip of what, there will be a lot to discuss and a lot to work out in these directions. But okay, what we have in mind is that, I mean, again, at zero further, it's, again, usual asymptotic states of QFT. They are BMS representations. They are what we call the hard BMS representations. However, by themselves, there is no way they can fulfill supermomentum conservation. It cannot be. So you're forced to consider other type of BMS representation, or other type of states. And as we understood in the last 10 years, the fact that the hard states by themselves cannot fulfill supermomentum conservation is related to higher divergences. That's the consensus of Weinberg's theorems. Now, maybe a strategy is that maybe if you're trying to construct a fully BMS invariant extension of QFT based on this other type of states, it might be that you could define some infrared finite S matrix, because it would just scatter states into each other, which in a coherent way. But clearly, if you want to do this, if you believe that this is meaningful, then this is this type of BMS particles that you would have to consider, as we discussed in the first place. Maybe we are not even thinking that BMS group is unitarily realized, but I think we should agree on what are the rules of the game and what we are expecting from the Hilbert space of gravitational scattering. again, one thing I want to emphasize is that the type of Fock space that you construct from these generic BMS particles is very different from what we are used to think in the literature, because in some sense, each of the particles come with its own soft charges. If you Fourier transform, each of the particles comes with their own gravity vacua. So it's different picture from what we might be used to think, that there are hard states and then there is a soft representation, which is the gravity vacua, and we are taking tensor product. Here, there is a lot more room for other stuff. Again, whether or not this is the way to go is to be clarified, but at least this is something which is coming up from representation theory. Okay, and with this, I think I will conclude. Thank you.
Thank you very much. Other questions or comments? Massimo.
Well, for BMS and especially for QED, there is a construction that gives finite S-matrix elements, not only cross-sectional. You can think of, say, Kibble, Fadeev, Coolidge, Chong, etc. So how does it fit here? I mean, it seems that you have not really used the information that comes from the existence of an infrared factorization of the S-matrix in your construction. And in a sense, how do you recover that in your language?
Okay, so yeah, thanks a lot. So first of all, again, something that should be emphasized about the classical Fadeev-Coolidge construction, which is especially emphasized in the work of Bob Wald, Prabhu, and Satish Chandran, was that there is something very specific about QED, which is the possibility to restrict inside your huge Hilbert space to the states which have zero charges, like zero hard charges, zero soft charges. This subspace is a very nice Hilbert space. It's separable. It has all sorts of nice properties. And this is the one that Fadeev-Coolidge used to construct something. But this Hilbert space, first of all, is unnatural because it means that all of your states always have zero charges completely. Like, again, hard charges on both charges. And, as I've been argued many times, it's much more natural to think of an Hilbert space with all, allowing for all possible charges. It's like fine-tuning your initial states in a very particular way. And also, this construction cannot work for gravity because having zero charges for gravity means you have nothing at all. You have no energy. So there is something very special about the Fadeev-Coolidge per se construction. Now, then apart from this, I agree at this stage, we are not using at all, in fact, any input from the scattering matrix itself. So that's why, I mean, there were two parts of the talk. This is motivations, but genuinely, this work was only about trying to extract as much as we can from representation theory. I guess now I think if you try to compare what we are doing with Poincare representation, you have a classification, but then you know that a lot of this representation you want to throw out. We don't want tachyonic representations. They are unphysical. We don't want continuous spins. We don't like them. So at some point, you need to have physical inputs, which needs to cut inside this forest of representation. I think this is where we are now, and this is very unclear what we are, exactly what's going to be the road. But I think you're right. Now we need to take some input from physics and try to cut inside this huge space of representations.
Maybe just a comment is that this infrared factorization a la Weinberg of about coming from the exchange of virtual soft photon, soft graviton, because everything he said, also there is an analogous story for QED, which works along the same lines. He didn't have time to talk about it. But all this Weinberg exponentiate factor, you can see it from the representation. So you can record this expression in this sense. And
maybe one thing something you could try to do is try to use all the kinematics there to construct some scattering amplitudes between amplitudes, BMS amplitudes, and maybe this can be done. Yeah.
Ben, again, in the same vein, the large U1 transformations are simpler than BMS. So have you done the classification?
We are working on this. I mean, essentially, the construction is the reason we started with BMS is that we had McCarthy that done a lot of things. In retrospect, it's obvious that you should not do this. You should start with the representation theory of large UN. I mean, we are working on this. We have a PhD student. I mean, essentially, the structure is the same. You have the details are different, but the whole structure is genuinely the same. So yeah, and I think that would be, as you're saying, I mean, this should be a right starting point to have some physical input would be large U1, because there you have much more control.
Which are the hypotheses for the theorem of non-conservation of supertranslation?
So what I'm to the conservation of alt charges. So, for example, what is behind is the following. If you just, well, I mean, in practice, the way you prove that it's not, is you take the difference. So you take a bunch of super momenta such that the momenta sums to 0. Okay? You take those, and then you just compute what this is. And essentially, this is a computation which has been done several times in the literature. What you get is the soft factor. So Weinberg soft factor, I mean, so another way of saying is that Weinberg soft factor is precisely the obstruction for conservation of super momenta in the process. So, yeah.
In a sense, my question was, for what kind of theories are we going to have this phenomena?
What I'm saying is, I think that's one of the reasons why this is maybe interesting. This is purely kinematical. So anytime you try, if you want to take Poincare particles, think of them as being BMS particles, then you can, but they cannot preserve BMS charges. That's, and in some sense, we know this for 10 years, but this is a representation theory statement of this. But the implication here is that you need to consider other type of representation, other type of states. No, it's nothing to do with gravity. Yeah, it's just a, it's just a kinematical statement that Poincare particles, when understood as BMS particles, they cannot preserve the charge. It's nothing to do with gravity. Sorry?
That was my
Yeah.
What I hypothesis.
Yeah.
Are for the non-conservative. Because I assume maybe that's wrong, that this has to do with the time dynamics. But maybe it's wrong.
No, really, this is purely kinematical statements that you cannot, usual Poincare particles cannot conserve BMS charges. That's just this statement. And then I think the dynamics is about what other states you want to allow for. This is where the dynamics should come in. What do you think? What type of other representation you want to consider? Again, as I tried to explain, there is a flurry of them. You need to cut in there, choose some. Maybe you don't even want to play by the rule of this game because you think that there is another symmetry, or BMS is so much broken that you don't want even to consider other states. But yeah.
Do you expect a similar story for subleading soft symmetries?
Okay, so very good. So representation of super rotations, BMS group with super rotations, they are, as far as I'm aware, very poorly understood. Very few has been done. In 3 dimension, a lot have been worked out by Glenn Barnish and Blagoji or Black. I think, but again, all the emphasis for them was on super rotation. So I think there is some interest about reading again their works in light of the stuff that I presented to get some flavor of, maybe if you want to understand how super rotation interacts with this arts of decomposition, I think you should start from that, from thinking this BMS3 story. In 4 dimension, the only works I know is work by Laurent Fredel, but is very preliminary. It's just they have been trying to use coadjuvant representation methods, which is far more difficult, and it's only there are some results, but they are very preliminary. Yeah. So I don't know, cannot say much. I think the question is well posed. It's just this very hard mathematical problem, looking for unitary representations of this huge infinite dimensional group. You see, here what's make it tractable is the fact that the infinite dimensional group has this semi-product structure, and it helps a lot in working out the classification. Yeah.
With relation to Andy's question, so I think a way of viewing this is trying to diagonalize supertranslation as a eigenvalue.
That's right.
But if you include superrotations and supertranslations don't commute, right? So can that be in principle done, like diagonalizing both things? Or should we look for other methods?
No, but this is the same, you see, this is the same problem we already here. Rotation, they don't commute with supertranslation. That's why you construct, that's exactly why wave functions, they are functions on the orbits, precisely because they don't commute. So you take some initial reference momenta, you act with Lorentz, you're producing a shell, and then your wave functions, the normalizable states, they are wave functions on the orbits. We are used to use momentum states because we know that at the end of the day we can do it, but genuinely normalizable states, they are wave functions on the orbit. So exactly, so from that perspective, the structure would be the same. I think you see the difference in the structure is that here, what really helps is that precisely these orbits, they are finite dimensional. So that's a huge simplification. You take a super momenta, you act with the orbits, it's just at most 6-dimensional. Your wave functions, they are functions on this 6-dimensional shell. If you do it with super rotation, then it's completely crazy because by definition, your shell is infinite dimensional. It's much harder question than what you're supposed to do.
Thank you.
Any other questions or comments? Okay, if not, let's thank Yannick again. There was nice presentation. There was another one?
There was a question.
If there was another one, apologize. No. Juan Paolo?
I mean, in the end, you have to compute the scattering amplitude. Can you use these formalities to compute the soft behavior of the scattering amplitude or not?
I think this is definitely right now. We didn't even try, but I think this is one game that we definitely are going to try is try to look for a generic scattering amplitudes for these BMS particles. How far do the kinematics constrain the structure? What can you say with these sort of questions? And there are natural questions. How far we can go? I think this is to be seen. It's natural game.
Yeah.
Okay, so
Yeah, sorry.
thank you very much. The appendix